suspended between a pair of NS5 brane, like this. Okay, the position of D4 brane corresponds to the choice of the vacuum. Now we turn on a string coupling and we let the string coupling very, very large. So we move to the M theory. So maybe you can guess what happens. You know, this brane construction turns into a single smooth M5 brane. Okay, so now let's discuss what's the shape of this object. What's the complex equation describing the shape of this object. So in order to describe this, okay, let's go back again. So NS5 brane is extending along x4 and x5 direction. So we introduce x4 plus ix5 like before. It is a complex number v, and also we have x6, and in M theory we also have circular direction, and by making use of that we introduce t. So the complex shape is characterized by one equation involving these two complex numbers. Okay, so now let's look in more detail into the situation. So we divide this object into left half, right half, and left half. And right half, so before introducing D4 brane, the NS5 brane is just described by T equal constant. But since we introduced N D4 brane at V equal AI, then the shape of the NS5 brane is changed into this form. So this equation describes the right half, and the similar equation describes the left half. And then what we have to get is some natural combination of this and this, and then the natural combination is this. And it turns out that this is precisely agrees with the solution obtained by Cyber and Witten. Okay, so brane construction is in this sense very useful. Actually, this way of deriving the Cyber-Witten curve is the quickest. In the old days, Cyber-Witten made use of a very complicated combination of consistency, homomorphy, duality argument to derive this equation, but using a brane, it's very quick.
How do you know the left and right branches gives you vector t and t minus 1? Do you have the large t and small t extension?
Why this is t and why this is t plus here? When t increases, I think x6 increases, right?
Right.
And when, so this equation shows that when v equals ai, t x6 goes to negative infinity. So it's like when v equals ai here, t is going to this direction. That's what this equation describes. Okay?
I see. Going opposite directions.
Yeah. So this equation gives you something like this. And this guy gives you something like okay. So in this way, our understanding of string duality and supersymmetric gauge theory became very, very fine. And we have now, after 20 years since the second revolution of superstring, we have a much finer duality equation. Are there any questions up to now? No. So up to now, we have been talking about sub-strongly coupled problem in gauge theory, and the M5 brane played a very important role. Okay, but still, our understanding about six-dimensional theory of multiple M5 brane is very insufficient. So this six-dimensional theory of multiple M5 brane is still mysterious. And the recent recent study is focusing on this six-dimensional 2.0 theory. Well, 2.0 theory, which is defined, characterized by the theory of multiple M5 lengths is known to have this property. So first of all, this is a 6-dimensional field theory, but we don't know how to write a Lagrangian for it. Or there are proposals about Lagrangian, but we haven't reached an agreement. Okay. And there are very, very interesting properties about this 2,0 theory. First of all, this 2,0 theory is labeled by n, just a number of M5 branes, or more precisely, we know of the existence of 2,0 theory labeled by ADE classification of the Lie algebra. And what is more important is that this theory doesn't have any adjustable, continuously tunable coupling constant whatsoever. So this theory is just labeled by integer or AD classification. And another important observation was that if we compactify this 6-dimensional theory on a smaller dimensional space, it turns out that we get many low-dimensional interesting fields. So let's look at this aspect by examples.
What does the 2, 0 stand for?
2, 0, well, that's a good question. So in 6 dimensions, there are, so this is a classification of 6-dimensional supersymmetry. 6-dimensional supercharge are allowed to have either positive chirality and negative chirality. And 2,0 means two units of positive chiral supercharge. So it's a 6-dimensional chiral.
Usually in the field theory you get coupling constants. Those are tunable, or some of them even carry dimensions.
Yeah.
But you don't have those. Are there some symmetries that is protecting those from appearing?
I think so, yeah, I think so. For example, if n equals 1, just a single M5 brane. But on a world volume of single M5 brane, we know that there exists a self-dual two-form potential. Gauge theory with 2 vector indices, and then the derivative of 3-form field strength, and the 3-form field strength has to be self-dual. So for self-dual theory, and the coupling has to be chosen at the self-dual value. Yeah, so. Right. So let's look at some examples of the compactification of 2,0 theory. So although we don't know what the 6-dimensional theory is, we know what happens when that 6-dimensional theory is compactified on a circle, for example. So if we take circle of radius R1, for example, we get 5-dimensional theory, and which turns out to be a 5-dimensional supersymmetric ambience, and the coupling is given by this. Okay, and we know this because we know, although we don't know the world volume theory of M5 branes, after compactification on a radius, circle of radius R1, what we get is n d4 branes, and the d4 branes support the supersymmetric case. Okay, and this is the Lagrangian and the definition of the field strings. Okay. Suppose we compactify one more direction. Okay, compactify onto S1 cross S1 of radii R1 cross R2. Then what we get is just a circle compactification from 5D to 4D, and then we get a 4D n equal 4 maximally supersymmetric ambience, and the coupling is given by the ratio, very interestingly, ratio of R1 and R2. Okay. Then the natural question will be, what happens if we change the order of compactification? So in the previous experiment, we compactified first on R1 and then R2. Then if we change the order of, if I compactify R1 and then R2, then we get the 4D superimage of coupling test. If we change the order, then we get the same theory but a different value of the coupling. What does this mean? Well, 4D superimage at the 2 different values of the couplings are the same. That's the natural question. Well, it turns out that for 4D n equal 4 superimage theory, there is a hidden quantum equivalence relation which inverts the coupling constant and exchanges the electric and magnetic particles. So this is very much like what we know in familiar electromagnetism. Okay, although we don't, although in the electromagnetism of our real world we don't have magnetically charged object, but if there is such a magnetically charged object, the electric charge and magnetic charge are reciprocal to each other by the famous Dirac quantization equation. And also here is this Maxwell equation, and if there are magnetically charged object, this guy is non-zero, this guy is non-zero, and this equation is symmetric under the exchange of E and B, right? And what we observed about the M5 brane in the previous transparency is just the explanation of this Monton-Olive duality. Okay. For this Payamil says Monton-Olive dual because the world volume theory of M5 brane compactified on S1 plus S1 doesn't depend on the order of compactification. Okay. So let me push this Monton-Olive duality further. So we derived this equation for the coupling. Coupling, four-dimensional coupling is just a ratio of R1 and R2. So when R1 is very, very small than R2, then the shape of the S1 plus S1 torus is something like this, very thin ring. So very thin ring corresponds to very weak coupling. Then if we change the ratio of R1 and R2, then the shape becomes something like this. And then around here, the gauge coupling is strongly coupling. Okay. So let's continue changing the ratio of R1 and R2 further. And what is going to happen is, as far as the shape of the two-dimensional torus is concerned, it goes back again to something which looks like a thin ring, right? Okay. But here, R1 is much, much bigger than R. But as long as the shape is concerned, the shape is corresponding to the very weak coupling, and indeed the four-dimensional theory is weakly coupled again, but in the dual description. Okay. Right. So far we have been talking about the rectangular torus, but we can generalize the compactification to some oblique thing. So the general two-dimensional torus can be defined by introducing two different periodicity. Z is equal to Z plus 1 and Z is equal to Z plus tau in a complex. And if we compactify M5 brane onto such a torus, then what we get is the four-dimensional supersymmetric annulus, the same, but with this value of the coupling. Now the coupling is complex, and the imaginary part is the gauge coupling, and the real part is what is called the theta angle. So it involves the instant density in the action. Okay, and the Monton-Olive, famous Monton-Olive duality says that the Yamil theory at the coupling tau and minus 1 for tau are the same. Okay.
So the coupling tau is complex.
Coupling tau is complex, and it takes value of the upper half. Yeah.
So the complex number means what? Just the theta?
Yeah, theta is real part, and I over G squared is the imaginary. So as soon as we consider the Yang-Mills theory with supersymmetry, it's very natural to combine the gauge coupling and the theta angle into this complex form.
Say again?
As soon as we consider the Yang-Mills theory with supersymmetry, it's very natural.
In the action, besides the QCD action, what else? The dot.
So as I said, four-dimensional super-Yang-Mills with any four supersymmetry.
Yeah. So
4 gauge nodes, 6 scalars. So they appear.
So this is not exactly the ordinary QCD. Okay. Yeah. This is the supersymmetric version.
Yes, it's a supersymmetric version.
Yeah.
And the property of this highly supersymmetric theory is very much different from ordinary QCD.
So the Montoning Olive theorem, okay, there's the theories at tau and minus 1 over tau are the same. Because that is only saying the 4D Susi Yang Mills.
Yes, Montonen
Not
Olive duality.
for the QCD.
In real QCD, there is no such a thing.
No such thing. Okay, so this is still not the.
Yeah, so this observation is not immediately applicable to.
Yeah, that's what I'm saying.
Yeah, we are just having fun about sort of highly supersymmetric. Okay. Right. So far we have been talking about the compactification of a torus, and then we get n equal 4 supersymmetric gauges. So it can be generalized by replacing a two-dimensional torus by more general Riemann surface, possibly with punctures. So this figure shows the Riemann surface with 3 handles, genus 3, and 4 punctures. And it turns out, this is a discovery by Gaiotto, that if we compactify n M5 branes on such a general Riemann surface, then in general we get 4-dimensional supersymmetric gauge theory with n equal to supersymmetry. And Gaiotto named the resulting 4-dimensional gauge theory like this, Tn of sigma. And n is the number of M5 branes, but already when n equal to 2, the theory is interesting. So let's restrict.
What is puncture?
Puncture is a small hole. The Riemann surface is smooth, but at some point we can introduce a small hole. For example, small hole.
I fall asleep. Do we discuss punctures before this page?
So this is the first place where the punctures.
So it's out of the blue. Why all of a sudden introduce punctures?
Why? Why? We can think about Riemann surfaces without any puncture, but
I mean, the puncture at least is not clearly defined, and if membranes have punctures, then what happens to topology?
Let me discuss a little bit about that point in the next transparency. So Gaiotto considered how the theories which can be obtained by wrapping M5 branes onto this multiple M5 brane onto this puncture Riemann surface. And first of all, we need to characterize the shape of this Riemann surface by some parameter tau. And tau contains the information about the length of the handles as well as the twist of the handle, as well and also the position of those punctures. Those parameters are contained in this shape. And also when characterizing the shape of the M5 branes wrapping this Riemann surface, generally the M5 branes are allowed to have some spiky divergence poles at each of the punctures. And then something like angles of this divergence is characterized by a complex number n. Okay, so these parameters define how multiple M5 branes are wrapping on the Riemann surface. And then starting from that M5 brane configuration, Gaiotto argued that we can get a 4-dimensional gauge theory. And this 4-dimensional gauge theory is a UV finite theory with n equal to supersymmetry. So the coupling appearing in the Lagrangian is a true parameter distinguishing the different theory. And in this gauge theory, it turns out that this MA turns out to be a mass parameter for the hypermagnetic particle.
Okay. The MA describes the pole position.
Pole position.
The spike. Would you say this?
Yeah,
spike?
the residue at the, not the position, but the residue at each.
And are the spikes corresponding to punctures?
yeah, at each of the spike, M fiber brain, at each of the functions, M fiber brains can develop spike. Yeah, so Guyot also gave the way to read off the Lagrangian given this general Riemann surface. Okay, so the way is as follows. Starting from this general Riemann surface, we can try to reduce, shrink this smooth shape into something like this. The structure made of tube and trivalent vertices. Okay, and this turns out to be a very, very weak coupling limit of the gauges. And once this has been made, we can easily read off the Lagrangian. I think I cannot explain to you how to do that in full detail, but at least if you have this diagram, then this has 1, 2, 3, yeah, I'm counting the number of internal lines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we get SU2 to the 10 gauge group. That's roughly speaking the group. And in addition, for each of the trivalent vertices, some matter fields show up. Okay, and the rough argument why each SU2 factor corresponds to each internal line is that, yeah, if you have internal line, yeah, we have 2 M fiber brains wrapping on this tube. Okay, so 2 M fiber brains wrapping on the tube is something like 2 D4 brains suspended between a M fiber brain. Okay, so each internal line contributes a gauge group. So this is roughly speaking the way to read off the Lagrange. Well, but maybe you may ask, the way to reduce from smooth Riemann surface to this diagram-like object is not unique. No, and indeed this observation is a very interesting fact. Yeah, so for example, let's consider the sphere with 4 punctures. Then you can easily think of the 3 degeneration limits: S channel, T channel, and U channel. Okay, so this consideration shows that for M fiber brains wrapping on this Riemann surface, there are 3 Lagrangian descriptions, mutually dual to each other. Okay, and also the coupling has a very mathematically precise relation with the shape of this 4-punctured sphere. Okay, so you can, if you wish, establish a very precise mathematical connection between the coupling describing this Lagrangian and this Lagrangian. Okay. Right. So starting from 2,0 theory, we talk about various possible compactification, and we get various interesting 5-dimensional and 4-dimensional gauge theories. Any questions?
Sorry, you mentioned some duality relations. Do they only hold only in the weak coupling theory?
This?
Yeah.
Here I talked about duality relation. Yeah, so, okay, so for example, this description becomes weakly coupling when this 4-punctured sphere is squeezed in this.
Right. My question is, what happens in strongly coupled limit? Do you usually have the dualities?
Oh yeah, so so if we do this, then this description becomes weakly coupled, but from the viewpoint of another description, it's a very, very strong coupling.
Oh, okay.
Yeah. So the relation is something like that. There are 3 different descriptions. The weak coupling in one description is a strong coupling in the other. But the relation is very mathematically precise. Right. Okay. So there are this many examples of possible compactification of 2,0. And more recently, we have found a surprisingly new way to compactify M fiber brains. And yeah, so let me talk about the AGT relation. So in 2009, it was found that some people computed the partition function of four-dimensional theory that we can obtain by compactifying M5 brane on a Riemann surface. So this is a four-dimensional gauge theory, and we compute a partition function on four sphere. Then very surprisingly, the result agrees precisely to the correlation function of two-dimensional Liouville theory at this special value of the coupling. And this Liouville theory is defined on sigma. So this is a rather mysterious agreement. And then, so Liouville theory is the theory of two-dimensional bosons, and there is a kinetic term, and in addition we have exponential potential. And the coupling appears in the exponent here. Okay, so this is a very interesting agreement between physical observables in four-dimensional theory and two-dimensional theory. And it is also known that if we increase the number of branes here, then instead of Liouville theory, we have Toda theory. Toda theory is also a two-dimensional conformal field.
So the coupling B, will it run? Is it a running coupling?
Coupling B that doesn't run. So coupling B characterizes conformal fields. And for example, this B enters into the formula for the center charge. If you are given B, you can compute center charge. And this interesting conjecture has been confirmed through the comparison of many interesting physical observables. And it has long been known that in two-dimensional conformal field theories, correlators can be evaluated rather algorithmically. And it has long been known how to compute that. But on the other hand, it has only very recently become possible to compute the partition function of Suzy series on the sphere. And this makes use of the localization theorem. So I gave a talk about the localization theorem this February, so I will not talk about it this time. Okay. So why this mysterious agreement happens? Well, so here is an interpretation. Yeah, so suppose we compute the partition function of the gauge theory on sphere. Okay, so the gauge theory, this gauge theory on the round for sphere. Well, then this partition function is also alternatively regarded as the partition function of two M5 branes wrapping this product space, Riemann surface and force. Okay, if we regard the sigma to be very, very small than force sphere, then we get four-dimensional gauge theory. Then we compute the partition function. But we can change the order of compactification like we did before. So let's, suppose we compactify on this force sphere first. Then what we get is something two-dimensional, some two-dimensional field theory living on sigma. And we are computing something like a correlation function of this sort. And then from the experience of computation of this partition function, we know that the result depends only on the shape of the sigma, not the volume or anything more complicated. Then if this guy depends only on the shape of sigma, then the two-dimensional theory living on sigma has to be conformally invariant. So from this argument, we roughly know that if we compactify M5 brane theory on a four sphere, what we get should be a conformally invariant theory, CFT. But after making a detailed comparison between physical quantities, we found out that this two-dimensional theory is a Liouville theory. Okay, so we found another interesting observation. Property. When M5 brane theories are compactified on S4, what we get is two-dimensional CFT, which is a very well-studied CFT. But if we choose the round force sphere, the coupling has to be a special value, 1. But some years ago, I and my my student made a further study of this case. And then if we deform the round sphere a little bit, by introducing a squashing paradigm, then it turns out that we can change the center, the coupling of the 2D total CFT by a general one. So, so